Hope you guys had a good end of the week. Happy Friday. Few quick announcements for you here. My office hours are now posted. Check out the syllabus. I posted an updated version of that on Carmen. They're going to be on Monday and Wednesday. Quick note about Jump, JMP, the software we'll be using for this course. I got an email from one of you guys. Thank you. If you've tried to download that already, you'll notice that there are two versions. Version 9 and 10 are both available. If you've already done one of them, that's fine. It doesn't really matter. The functionality is about the same, but go with 10 if you haven't done that yet. And I made a note about that on the syllabus as well. And then first homework assignment is due next Friday, so that's going to cover just these first 3 introductory sections, which we should finish up today. So there should be plenty of time for you guys to work on that. But just a heads up that that's coming. The homework assignment is posted on Carmen as well. Questions, comments before we jump in today? Everything going all right? Good first week of class? Short week, I guess. All right. Well, if nobody's going to say anything to me, we'll go ahead and get started. That's fine. Again, we're going to pick up with Chapter 2 where we left off on Wednesday. And this should be, the slide after this should be about on the middle of page 4 of your Chapter 2 notes. But just anyway, you remember we started out talking about some set operations, some sort of basic tools that we'll use in this chapter, and then we moved on to the idea of probability and kind of trying to very formally say what probability is and what some of our rules are for how we can calculate these things. And so the very foundations of probability that we'll use in this class are actually based on these 3 axioms, which we discussed on Wednesday. Everything else that we need to use can actually be derived from these 3 things. But these are the 3 things that you kind of have to assume before we go any further. So we just need, for any event A that we're looking at, we need the probability, of course, to be bigger than or equal to 0. You can't have a negative probability. S is our sample space, so the probability of the entire sample space happening is going to be 1. You have a 100% chance that something will happen. And then if we have mutually exclusive or disjoint events, so events that have no intersection, so that's what I mean by disjoint or mutually exclusive. The probability of a bunch of unions of those things is just the sum of the individual probabilities. So an example of this would be the probability of A union B is the probability of A if A and B are disjoint. So again, just some basic rules here that we're going to use to establish some other rules that we can use, that we will need to use quite regularly in this chapter. All right, so here we go on page 4 of your notes. Using those axioms, the first thing we can prove is that the probability of the null event, so again, this little thing here is the null event. The probability of that happening is actually 0. So this is based on the first axiom from the previous page. So again, we can write that the sample space S is equal to the sample space together with the null event. Because remember, the null event has nothing in it, so if we take the union of anything with the null event, we just get back the same thing. And also, the sample space intersected with the null event is equal to the null event. When you take the sample space and intersect it with something that has nothing in it, you'll get something that has nothing in it. So we already saw that the probability of the entire sample space is 1. And we can, from this thing here, we can say that this is also equal to the probability of S union empty set. And because those 2 events are disjoint, this is equal to the probability of S plus the probability of the empty set. And therefore, probability of the empty set is equal to 0. So again, that's kind of an intuitive result, but there's kind of our formal way of proving that is actually going to be true. So the probability of the entire sample space is 1. The probability of the null event is 0. Sort of along the same lines, we have the second proposition for any event A, the probability of A is equal to 1 minus the probability of A complement. So remember this, this is A complement is the opposite of A. So it's everything in the sample space that's not in set A. So this is kind of an easy proof again as well. We can write down, of course, the sample space is equal to A together with A complement. And just like before, these two events, obviously A and A complement, are disjoint. They have nothing in common. Their intersection is empty. So probability of S, which is 1, is going to equal the probability of A union A complement. And because they're disjoint, we can just take the individual sum of those things. And then if you rearrange some things, you'll get that probability of A is equal to 1 minus the probability of A complement. See what we're doing here? Is this okay with everybody? And always feel free to flag me down if I'm going too fast or anything. Again, these sort of two simple ideas here, obviously they kind of make sense, but it's kind of very formally stepping through how we actually prove these things. Alrighty, there's our first two propositions. Moving on here. For any two events A and B, so these events A and B can be anything, the probability of A intersect B complement is equal to the probability of A minus the probability of A intersect B. Okay, so how do we go about proving this? Well, I think first of all, it's sometimes interesting to, or it can be helpful to draw a picture again to kind of see what it is that we're looking at, and use that as sort of our basis for moving forward with sort of a formal proof here. So if we do our favorite Venn diagram here. So there's our event A and B, and our sample space is that entire square. What shape on that Venn diagram that's colored in would represent A intersect B complement? So if I want this set right there, ignoring the probability for a minute. Yeah. Yes, exactly. So it's this part of A here. That does not include B. So it's taking everything of A that's not in B. That's not in B. And so maybe now you can kind of see where this comes from, right? It looks a little more obvious now. If we want the area of that green thing, we can take the entire probability of A and subtract off that little football shape, which is the intersection there. So that's this color here would be. So if we want the entire probability of A, or if we want just the green section, we can subtract off the blue section. So that's our visual proof, which is, of course, not a proof at all. So let's actually go ahead and do this. So again, we can write down, using some tricks here, we can say that A is equal to the intersection of the union of two sets. So A intersect B together with A intersect B complement. So I'm kind of figuring out a fancy way to write out what that set A equals. We can put two things together. The first one is A together with B, so that's the blue shaded area, and then we want to add in everything else that's in A but not B, so that's the green area there. And again, same trick as before. We can now note that A intersect so we can write, sorry, here we're looking at the wrong line on my notes. We can write A intersect B together with A intersect B complement, there's nothing in that, right? So if we intersect those two sets, they don't overlap, they're disjoint. So again, now we can just, since we have disjoint sets, we can just add here. So therefore, the probability of A equal the probability of A intersect B plus the probability of A intersect B complement. And you can do some slight rearranging there to get the proposition back. Is that okay with everybody? Are we all on board? Again, just kind of rewriting things, and rewriting things in such a way that we have disjoint events allows us to use that addition trick. So when we have two events that are disjoint, we can just, if we want the probability of their union, we can just take the probability of each one and add them together. Okay, getting more complicated here as we go. This leads us to something called the general addition rule. So now for any two events, A and B, if we want the probability of their union, what we can do is we can take the probability of A plus the probability of B. So if this isn't here, that would be true if A and B are disjoint, right? That's what we've been doing for the last few propositions. But now we don't have to have them, if they're not disjoint, we still have a rule of figuring out what their union is. So we can just subtract off now what their intersection is. So again, let's start out by drawing a picture here. There's our sample space. Here's A and B. Again, what's the set shaded? What would I have to shade in for A union B on this diagram?
The whole thing.
Whole thing, right? Yeah. So I want let's change colors. I would want this entire thing here. So now we can see that if I take the probability of A, it's going to be this entire circle here. And if I take the probability of B, I do that entire circle. But now I have this little part that the football shape area that I've counted twice. So I want to subtract that off. I don't want to count that twice. If I subtract it off, that will give me the probability I'm looking for. So that's the picture is your intuition, but again, let's kind of formally figure out how we can prove this to be true. Again, we want to use some tricks again. Again, we can note that the union of A and B is equal to A together with B intersect A complement. So I'm taking A, so I'm leaving A as it is, but then I'm going to union that. Instead of B, I'm going to take that with B and A complement. So that's again just this sort of this moon-shaped area over there. But again, I have the same area, right? So that's okay. But I can also write I can also note that these two sets are disjoint here. So I also have that A intersect B intersect A complement there's nothing in there. That should be pretty straightforward. And so now I can use some fancy tricks here. Now that I've had my fancy tricks, I can write this down. So now the probability of A union B, since those two events are disjoint, it's the probability of A union. I haven't changed anything yet, but since they're disjoint, I can now make this the probability of A plus the probability of B intersect A complement. And now I can use proposition 3 to change the last thing on that. So again, this is probability of A, but now to go from here to here is proposition 3. This is equal to the probability of B minus the probability of A intersect B. So kind of piecing together some rules here to give us sort of general rules that we'll want to use. So when we get to the end of this chapter, I'll sort of summarize some of these things for you, but maybe put a little asterisk by proposition 2 and 4. Those are ones that you probably will use quite regularly. 1 and 3, maybe not as much directly, but they are always true. Everybody okay on what we're doing here? Am I going too quickly or anything? Okay. Well, enough of propositions. Let's actually try to do an example and see how we can apply these propositions. So here in this example, we're talking about electricity usage. So we have a utility company offers a lifetime rate to any household whose usage falls below 240 kilowatt hours during a particular month. So we're offering lifetime rates to these people. And so let's let A denote the event that for a particular household in this community, that they do not exceed the lifeline usage during January, and let B be the same thing, so that they don't exceed the 240 kilowatt hours in July. And we're just going to throw some numbers at you, assume that these are true. I suppose that the probability that they don't exceed in January is 0.8, probability that they don't exceed in July is 0.7, and the probability that they don't exceed in both months is 0.9. So, again, we're not talking about where these numbers come from, but we're just going to assume those and see how we can apply these things. Okay, so let me just jot down probability of A is 0.8. Okay, so now if I want the probability of A intersect B, anybody have an idea on how I might, using just that information that I have? Anybody have an idea? Yes, sir.
You do the A union B equals the probability of A plus the probability of B minus the probability of A intersect B.
Very nice. Yeah, so I can take my general addition rule and just sort of rearrange things and get the right thing here. So again, we know the probability of A union B is equal to the probability of A plus probability of B minus the probability of A intersect B. So I know 3 of those numbers, which means I can easily solve for the other ones. So that means this is going to be the probability of A plus the probability of B minus the probability of A union B. Which, if you do some math there, should be 0.6. So again, very, very straightforward there. Again, just kind of using that general addition rule and rearranging some things to get to be able to use the information that we have. It's not the only way you could calculate that, obviously, but with the information that we have, it is the only way that you could find that. Okay. Slightly more complicated here. Let's find the probability that the lifeline usage is exceeded in exactly one of the 2 months. So I'm going to draw a picture. We'll see if we can pick out the correct shaded in area. So this is event A, this is event B. It's our sample space. So if I want the probability that the usage is exceeded in exactly one of the 2 months, what would my shaded area on this Venn diagram be? Yes.
Either the union of A and B minus their intersection.
Exactly right. So I want to leave out the chance that they or the cases in which they are exceeded in both months. So I want, as was just said, I want A union B minus their intersection. So you can take these 2 sort of moon-shaped pieces there, and I need to figure out what that is. Any ideas? Yeah.
A plus B minus the intersection.
A plus B.
Probability of A plus probability
Right.
of B intersection.
So probability of A plus the probability of B minus the probability of their intersection. So that'll be everything in there, right? That's my general addition rule. This is
Minus 2 times.
okay, minus 2 times. Yeah. Okay, so that's getting closer. Let's write this. That's very close, and that's what we'll get to. But let's write this down. So again, this shape here is we want A intersect B complement, right? So that's shaded in areas. Everything in A that's not in B complement, not in B, and similarly over here is B intersect with everything that's not in A. So I should not have erased what I just did, but so if I want the probability of A intersect B, again I want to take that union with probability of A intersect B, other way around, B intersect A complement. Again, I have the probability of one event union with another event, so I can use my general addition rule here. Plus probability of B intersect A complement minus the intersection of these two things. So A intersect B complement intersect A complement intersect B. So I'm just using my general addition rules here, show you kind of a different way to get to the same answer that was just given. So what is this probability right there? Zero, right? Those two things have no overlap. So we can get rid of that, and then this other one we can use that second proposition, or the third proposition, excuse me. So this is A minus probability of A intersect B plus probability of B minus, and that is of course exactly what was just given to us. This is probability of A plus the probability of B minus 2 times their intersection. So if you can just see that that's what it should be, that's fine. You don't need to go through that whole song and dance there. Just wanted to kind of write that out. Now we can say what this is: 0.7 plus 0.8 minus 2 times 0.6. Should be 0.03. 0.3. So a good way to check is if you get something that's bigger than 0 or less than 1, then you've done something wrong. You need to kind of reevaluate there. Questions, comments? Everyone okay with what we're doing here?
You mean less than 0 and bigger than 1?
Sorry, yes, less than 0 and bigger than 1. Yep. So again, maybe this convinced you that a picture is a good thing to draw. I think it can help you really see when you're dealing with sort of simple things like this, where you just have 2 or maybe 3 events. You can kind of shade things in there and figure that out, and then start applying some of the rules that we just discussed. Okay, moving on to section 2.3. We're going to talk about some counting techniques, which is where it starts to get fun in here. So if you remember from the previous section, when we talked about sometimes it's best just to, when we have a certain number of outcomes in our sample space, rolling a dice, we had six outcomes, of course. We can just make all those outcomes equally likely. So if our event A has 3 things in it, then so if A is rolling an even number on a dice or something like that, the probability is just 3 out of our total number of outcomes, which is 6. So sometimes as we've seen so far anyway, we can actually list out what all the outcomes are and count those by hand, but that won't always be the case. Quickly, here's an example where we can do it, although you'll already see it's getting more complicated. So now suppose our experiment is we're going to roll 2 6-sided die. And our sample space consists of the 36 possible simple events. So if we roll 2 dice, we're going to get something that's in here. Either the first one will be a 1, the second one will be a 3, or so on. So that's in your notes there. So what's the probability that the sum of these 2 rolls is a 7? So if we let A equal the event that the sum of the 2 rolls is a 7, what's the probability of getting a sum that equals 7 going to be there? Yeah, right. So you can pick out the ones in here in which you get that 7, right? And that's 6 out of the total 36 possibilities, or 1/6, as you guys said. So that's great. So it's in a situation like this, it's pretty straightforward to say, okay, here's what I want to know about. I can actually just count what all the outcomes there are. So here, n is 36. It's not that bad to actually write out everything. I mean, you probably wouldn't want to do that, but you could. But when n becomes 100 or 1,000 or anything really bigger than that, you definitely don't want to write all the things out. So we can use some kind of general rules to compute probabilities for these equally likely outcomes without actually listing all the outcomes out. And so some terminology here down at the bottom is, we're going to call this thing a k-tuple is an ordered collection of k objects. So a double, triple, after we get past 3, we want to use the generic k there. But the key idea here is that this is an ordered collection of objects. So in Wednesday we had a question on one of the examples, does it matter if is a head and a tail different than getting a tail and a head? If we're talking about this, then yes, that would be a different sequence. So if you have a 4 tuple, have that 1, 3, 2, 4 is different from 4, 3, 1, 2, even though the same numbers are in both of those things. So key thing is here is for this first. We'll later look at unordered collections, but now we're going to start with looking at things that are ordered. And our general rule for ordered k-tuples is that if there are n1 choices for the first element, and for each choice of the first element we have n2 possible choices for the second element, and so on all the way down to the nk choices for the last element, then the total number of possible k-tuples that you can get is just the product of all those numbers. So n1 times n2 ... times nk. So if you want to find the number of k-tuples you can have, that's how we do it. So let's do a quick example. Maybe Five Guys fans in here, but if you go there for a burger, we suppose here that there are 2 types of burger. You can get a hamburger or a cheeseburger, 2 sizes, regular and little, and 16 different toppings to choose from. So how many possible 1-topping burgers are there to choose from if you first order the burger, then the size, and then the toppings? So we have 3 things we want to choose here, right? We need to figure out what burger we want, the size, and then the topping. So this will be a 3-tuple. And so how many choices of burgers do we have? Well, we have 2 choices for the burger. We have 2 choices for the size, and we have 16 choices for the toppings, which gives us 64 possible combinations. You have so many choices when you go to Five Guys. Did you guys know that? So just kind of, here's what I mean by a k-tuple. So here why does order matter here? So it's a little different than just having numbers up there.
Toppings for a burger you haven't ordered yet.
Yes, right. So each place there. So I would have a collection of 3 things, right? I'd have a certain burger, a certain size, and a certain topping, and those each correspond to specific things, right? So I can't. There's not 16 different burgers to choose from or something like that. So order does matter here because we have specific categories that we're looking at. Okay, so some more terminology for you here. Something called a permutation is an ordered subset. So this is kind of the same idea as a k-tuple, but it can possibly be a subset of that. So the number of permutations of size k that can be formed from n individuals or objects in a group will be denoted by this thing over here. So capital P with subscript of k and an n there. So now we're kind of in the world where we have the same number of things for each category. So if, for example, I'm choosing students in this room, if I want to choose 3 of you, how many ways can I do that? I have a certain number of you to start with, and I can kind of go from there. So if my sample space is just the first n integers, 1, 2, 3 up to n, again, just to note that 1, 2, 3, 3, 2, 1, and 2, 3, 1 are different permutations. So again, order does matter here. Of course, those are not the only permutations of size 3 from that list, but just when I say permutation, I'm talking about something in which the order does matter. So it's ordered. Okay, so consider again our sample space here, kind of simple example so far. How many permutations of size 1 are there? So if I have n different objects and I want to take subsets of just 1 from them, how many of those do I have? N, right. So I have n total objects in my sample space there. That's pretty straightforward. How about of size 2? So if I now want to take 2, yes, so what did you say?
N plus n minus 1?
N plus n minus?
1 time.
Or times, yeah.
Yeah, so we want to take n times n minus 1. So again, for the first, if I'm choosing 2 things, the first one I have n total possibilities. That's just like in the first bullet there. But then choosing my second object, I don't have n choices anymore, right? I've already chosen one person out of there, or one object, so I only have n minus 1 yet to choose from. So n times n minus 1. It's kind of going back to that idea. N choices for the first one, n minus 1 choices for the second one, so I just multiply them together. So more generally, we can kind of extend this if I want to know a generic k. So there we did k equals 1 and k equals 2. For any other k, there's a general rule. So there's all those different ways to select the first k items, and then I can multiply all those things together to get the total number of possible permutations of size k from a set of size n. So I'll just take n times n minus 1, and so on until I get down to n minus k plus 1. And we can actually introduce some more notation that will help us a little bit. This idea of factorial notation. You guys seen this before? I'm sure you have, many of you. So n factorial, we're gonna denote using an exclamation point. It's a really happy n there. And just what that means, I'm going to take n and multiply it all the way down, subtract one number at a time, and go all the way down to 1. So n times n minus 1 times n minus 2, and so on down to 1. And then just a caveat, note that if we take 0 factorial, we're going to define that to be 1. Although that does kind of make sense. There's only one way to select 0 objects from a set. So our shortcut for finding our permutation of k items from n total items, we're going to say is n factorial divided by n minus k factorial. And so let's kind of show why this is true. Again, what we saw before was that this is equal to n times n minus 1 times n minus 2, and so on down to n minus k plus 1. So that's what we said it was before, but we can now write out what this thing up here equals. This n factorial is equal to n times n minus 1 times n minus 2, and so on, down to n minus k times n minus k plus 1, and then all the way down to 1. Similarly, I can just n minus k factorial, sorry, this is a minus 1. This is n minus k times n minus k minus 1, and so on all the way down to 1. And the second part of those, the denominator cancels out with the second part of what I wrote on the top, on the numerator, and there you have it. So that's going to be our shortcut for figuring out what these, how many permutations we can get for a certain k and a certain n. Just take n factorial divided by n minus k factorial. Of course, special case is when k is equal to n. So in our notation, we have n items. We're choosing n items out of n items. So this is n factorial divided by n minus n factorial. Just n factorial over 0 factorial, which is just n factorial over 1. So then we're kind of back to our definition of what a factorial is there. Everybody okay so far? Everybody with me? Okay, so let's do an example here. Suppose that there's a few more of you than that in here, but suppose there's 50 of you guys in this class, and I want to have 8 of you, but have you sitting in the front row. So suppose there's 8 seats in the front row. How many different ways can I find such that I have 8 students sitting in the first row? And we're going to further assume that each seat is numbered or something like that. So we have different orders of students in the first row are different. So here order does matter. What we want here is we want a permutation of 8 students out of 50. So our rule here is this is 50 factorial divided by 50 minus 8 factorial. And of course, what we know what that means, it's 50 times 49 times 48, all the way down to 43. And that is a very large number. Very large number. Lots of different ways that we could do that. So I don't know, have you guys ever tried punching factorials into your calculator? So you could of course punch the numerator and the denominator of that thing in separately, but when those numbers get bigger and bigger, your calculator is going to give you an error, so you'll need to use the little shortcut that we have there. Anyway, that's how many ways I could put 8 people out of 50 in the first row of a classroom. Questions, comments? We all okay? Going too slow, too fast? Forge ahead then. All right, so that's those are permutations. Those are ordered subsets of a list. Sort of the other side of this is something that's called a combination. So this is an unordered subset. So this is now, it's the same idea. I'm still going to take k items out of my total n that I have. But now, as we see down here in this example, subsets 1, 2, 3, 1, 3, 2, 2, 1, 3, and so forth, those are all the same combination, right? Because they have the same objects or individuals are in each of those things. So now I don't care what order they go in. I'm just thinking about how many ways I can choose that many out of k out of a larger group of n. So permutation order matters, combination order does not matter. These are unordered subsets. And our notation will change slightly. We're going to put n k inside parentheses. Make sure to not put, it's not a fraction, so don't put a little fraction bar in there. But that's going to be our notation for a combination. Okay, so kind of thinking about this a little bit more, if we're selecting k items from n total items, if we don't care about the order, then if we calculate it in the same way as we did with permutations, that's going to overcount the number of ways we can do this, right? Because here we see that those 6 permutations there at the bottom are equivalent to just one combination. So we need to change our formula just slightly. So if our sample space is just 1, 2, 3, and we want to choose 2 items out of that, again, we know we have 6 permutations, right? 3 choices for the first one, 2 choices for the second one, 3 times 2 equals 6. And there they are. However, if order does not matter, then 1, 2 is the same as 2, 1. And same for those other three pairs there. And so that means that I just have 3 combinations, 3 different unordered sets there. To kind of give you the intuition there. So I'm overcounting, so I need to divide by something more than I did before. Turns out I need to divide by an extra factor of k factorial. So n choose k, and again, I didn't say this, but we'll read this. The n over k inside the parentheses, we're going to read n choose k. We're choosing k items from n total. Is equal to the permutation of the same numbers, but now we're going to divide by that extra factor of k factorial. So we're going to have fewer combinations. Always have fewer of them than you do permutations. So again, same example. Suppose now I have 50 students in a class, but now I don't care about the order that they're sitting in the front row. So I just I want to take 8 of them and see how many, and sit them in the front row. This is going to be now 50 choose 8, which is going to be 50 factorial divided by 42 factorial times 8 factorial. So this is 50 times 49 all the way down to 43. That's my permutation. That's the 42 factorial on the bottom cancels out the rest of that thing. And now I want to divide by 8 times 7 times 6 all the way down to 1. Still a very large number. I have now 536,878,650 different ways. So that bigger number that we saw before, that was if I care about what order the front row is sitting in. Here, I don't care about what order it is, and it's still a giant number. All right, so this is our definition for calculating combinations. We know how to do permutations as well. Let's do a fun example to finish out this section. Going back to our gambling examples. So now we're looking at maybe poker here. We have a standard deck of cards, as we all know, contains 52 cards, 13 cards each of 4 different suits. So we have clubs, diamonds, hearts, and spades. So first question, very very generically, if you're playing 5-card poker, how many 5-card hands can we make here? So first of all, if I am dealt 5 cards, does the order matter here in this case? Order does not matter, right? Because if I have king, ace, 9, 10, 3. That's the same as if I got them in a different order. I don't care what order the cards are in. I just want to know how many different ways I can do that. So unordered means I'm going to do a combination, right? So there's 52 total cards, and I want to choose 5 of them. So 52 factorial over 52 minus 5 factorial times 5 factorial. And we can just write down what our rule here is. Again, there's a lot of different cards, different hands that you could get. 2,598,960. All right, so what's the probability of getting a hand with 3 red and 2 black cards? What would my strategy possibly be here? So if there's that many total hands that I could be dealt, we're assuming that each one of those hands is equally likely. What's my first step in figuring out a probability of a certain type of hand?
Split the sample space into space for red and black cards.
Yes, so I'm gonna divide the cards into, thinking about in my mind, I have some red cards, I have some black cards. So we need to figure out what those are. I guess that's a great point. And then I need to figure out how many ways I can get 3 red cards and 2 black cards in my hand, right? So for those of us who maybe aren't familiar, clubs and spades are black, and diamonds and hearts are red. So we have 26 black cards and 26 red cards. And since I want 3 red cards and 2 black cards, I can multiply those 2 numbers together. So if I figure out how many ways I can choose 3 red cards out of the 26, and then I can multiply that by how many ways I can get 2 black cards out of the 26 black cards. So what I want here is the number of to get 3 red out of 26, and then I can multiply that by the number of ways to get 2 black out of 26 as well. Does that make sense? So that'll tell me the total number of ways that I can get 3 red cards and 2 black cards. Does that make sense why we would do it that way? So now we're kind of back in the same boat that we were in the first part of this question. So this is going to be, we have 26 red cards. We want to choose 3 of them. We're going to multiply that times the 26 red cards and choosing 2 of them. So skip through the steps of actually writing what those are. This is 2,600 times 325, which is 845,000. So then what's my probability of getting 3 red and 2 black? Right, so I have 2,598,960 total possible ways that I can, total possible hands that I can get, and here we've just found that 845,000 of those give me the outcome that I want. Those give me the 3 red and 2 black. So the probability that I want, I can just divide those 2 numbers, and I'm running low on space here. So let me write up here at the top of the next slide. Probability of getting 3 red and 2 black is going to equal that first number, 26 choose 3 times 26 choose 2 divided by 52 choose 5, and that is 0.3251. So that's not necessarily a particularly good hand, but there's a pretty good chance that you'll get about a 1 in 3 chance that you'll get a 3 red and 2 black. Everybody with me? Is that okay? All right, let's get a little more specific here. Last question here. What is the probability of getting a flush, which is all 5 cards of the same suit? So I want the probability of getting a flush. So we're going to have something divided by something else. I'll do the easy part. Our total number of cards, 5 card hands that we can get is that 52 choose 5. What do I want in my numerator here? Yeah.
You do 2 times 26 choose 5.
2 times 26 choose 5. Very close, very close. So that would be of getting 5 cards with the same color, right?
Oh.
Yeah. So we want 5 cards of the same suit. So.
It'd be 2 times 13 choose 5.
Yes, exactly. So in many cases like this, it's kind of good to start small. So let's first think about how many ways can I get 5 cards of, say, hearts. 13, right. So if I want all 5 cards of hearts, for example, that would be I have 13 hearts cards, so that's 13, and I want to choose 5 of those. But now I didn't ask for just hearts. It can be any suit. So. What else? Again, how do I change that to be, yeah.
Suits are mutually exclusive, so you can just take that out, the product of all the suits.
Exactly right. So we could just add this up 4 different times, right? So because as you said, each suit is mutually exclusive. So if I want, so probably I can just add those up. So that would be 4 times 13 choose 5. Would be correct. There's a slightly different way to figure out what that numerator is. So instead of sort of thinking about it that way, I think it's maybe a little more straightforward to think about. So I have 4 possible suits, right? And I just want all my cards to be one of those suits. So the extra number I can multiply on top there. I have 4 possible suits, and I just want to choose one of those suits for my flush. So you can check 4 choose 1 is in fact 4. So that's the same answer there, but that's maybe more intuitive way of thinking about how to get there. So let me tell you what this is. This is 0.002. Little smaller chance of getting a flush. All right, so these counting problems can be very tricky. So just kind of think through what my options are. We'll do some more practice with these later. But that brings us to the end of lecture. Thank you guys so much for being here. Have a great weekend, and we'll see you on Monday.